All right, so let's look at how you go about doing this one. Stoichiometry, how to recognize, regardless of this, that I need to be doing balanced equations and conversions with moles. It's because it gives me an amount of one chemical and asks me about another different one. So it says how many moles of this can be made if I use this amount of this. So first, let's start with an equation. What do? Balanced equation, first thing. How many moles of this can be produced? That tells me right there NH3 is made. Using that combined with that tells me that, let me just straighten out the camera. There we go. Anyway, yeah. So it tells me that H2 combined with N2. All right, look. Hydrogen, hydrogen, nitrogen, nitrogen. You know, it's workable. All right, 3 hydrogens, 2 hydrogens. My little shortcut, I'm going to put this 2 right here. I'll put this 3 right here. What that means is now I have 6 hydrogen, and this makes 6 hydrogen. That's 2 nitrogens. Oh, look, 2 nitrogens. Okay, that's good. All right, so that's my balanced equation. That's step 1. I'm given moles, and I'm asked for moles, so this is actually going to be pretty straightforward. So 1.40 times 10 to the third moles of H2. When it says excess N2, all that means is like that there's enough of this that I don't have to worry about it. There's plenty of extra, it's not going to run out, so I can just focus on this. Anyway, it gives me that as my given, and then I need a conversion factor. I know I need moles of H2 on the bottom so that moles of H2 can cancel moles of H2, and then on the top, I need moles of what I'm trying to find. Because if I have moles on the bottom, then I can put, and I need moles for my answer, then I can put moles of NH3 because I'm being asked for moles of NH3, so I want it my answer. And can I have a relationship between these? Yes, I can. It comes from the balanced equation. Look, there's 3 moles of H2, so I put a 3 right here. NH3, look, there's 2 of them, so I put a 2 right there. So I'm just taking this times 2 divided by 3. So let's do that. Reminder. There we go. Use parentheses for your scientific notation so that you don't have to worry about wrong order of operations. So 1.40 times 10 to the third. Notice I didn't push the times button. That's important. Anyway, times 2 equals, divided by 3 equals. That's my answer, 933. And, let's round that to the right number of sig figs. This is infinite sig figs. That's 3 sig figs, so I'm going to get 3 sig figs out of this too. 933 moles of NH3. All right, so that's how you handle that one. Let's see. All right, let's there we go. Let's do this one. What mass of oxygen is required to react with that amount of methane? This is a combustion reaction. Oxygen react with methane. When it says combustion reaction, you need to remember combustion means catching on fire. When you burn something, it means it reacts with oxygen. So there you go. Remember, anything containing carbon produces carbon dioxide as a product. Anything containing hydrogen produces water as a product. So that's why it has CO2, that's why it makes H2O. All right, that's combustion. So we need to balance this for starters. Got 3 oxygens, got 2 oxygens, that's a problem. That's complicated. Let me do some other ones. So 1 carbon, 4 hydrogens. Okay, let's put a 2 here. So that's 2 hydrogens, or 2 times 2 is 4 hydrogens. So we're good with hydrogen, still good with carbon. What about oxygen? I've got 4 oxygens present. So let's put a 2 here, and now I'm good. All right, that takes care of balancing. Now I can do what mass of oxygen source, and this implies units of grams. So in other words, I need to find grams of oxygen, and I'm given grams of methane. So 45.63 grams of CH4 times, and then I need grams of CH4 on the bottom. That way grams of CH4 cancel CH4. We always, when in doubt, convert to moles. There's my moles of CH4. Now that's not my final answer. I want grams of methane as my final answer, so I need to put moles of CH4 here so it cancels. or sorry, I don't know why I said grams of methane. I meant to say grams of oxygen is my final answer. But because oxygen is what I'm being asked for, I need to go from moles of what I'm given to moles of what I'm trying to find. By the way, this is a pattern. If you're given grams, then you go from grams to moles of what you're given. And you're always going to go from moles of what you're given to moles of what you're trying to find. And then the last one is if it asks for grams or some other unit, then this will be where you go from moles of what you're trying to find. I don't know why. Yeah. Moles of O2. And then grams of O2. So tell me how many grams of O2 are needed to react. Okay, so that is my setup. That'll give me the answer I desire. I need a molar mass for each of these. I need to show work. It is important to show you work for your molar masses. So CH4, that's 12.01, that's 1 carbon, and then 4 hydrogens. All right, let's get that. And that's 16.04 grams per mole CH4. Same thing for O2. 2 times 16.00 equals 32.00 grams per mole oxygen. All right, so, well, got that. Let's do this now. CH4. By the way, I didn't box these because it's not my final answer. 1 mole of CH4 has a mass of 16.04 grams. So that's why I put that. This is the mole ratio from the balanced equation. There's a 2 next to the O2, so I put a 2 there. There's nothing next to CH4, so I put a 1 there. And then for the O2, 1 mole has a mass of 32.00 grams. That's what a molar mass is. It's the mass in grams of 1 mole. All right, time to calculate. 45.63 divided by 16.04 equals, times 2 equals, times 32 equals 182. Point whatever. How many specifically, though? 4 sig figs. 4 sig figs, 4 sig figs, infinite sig figs. So I'm going to round that to 4 significant figures. 182.1 grams of O2. Yeah, that way I can make sure it's not actually mistaken for a decimal. That's how much is needed. Okay, onward. Let's do this one. How much bromine is required to react with zinc metal? Okay, bromine reacts with zinc. There you go. Reminder, diatomic element. To produce zinc bromide. Zinc bromide. By the way, in case you don't remember how to find the formula, zinc is a 2+, bromine is a 1-. So that's going to produce 1 zinc and 2 bromines in the formula for ZnBr2. And then, let's see. So let's check to see. We got 2 bromines, 1 zinc, 1 zinc. It's balanced as written. We're good. All right, that's the balanced equation. 15.0 grams of zinc metal to produce zinc bromide. How much bromine is required? Okay. 15.0 grams of zinc times, we're going to put grams of zinc on the bottom so I can cancel with grams of zinc over there to give moles of zinc. And then we need moles of zinc here so that I can cancel that because moles of zinc is not the answer. We want to know how much bromine. By the way, when it says how much, I'm going to look for grams because if it doesn't specify it, then I reply with the same units given. So anyway, what I was saying, moles of bromine is required because, again, it's asking for bromine. And to repeat, I know I'm not going to stop here because when it says how much and it doesn't specify, it gave me 15 grams. So if it gave me grams, I'm going to reply with grams unless otherwise directed. So I'm going to put moles of bromine here because it's not my final answer. And oh, I forgot to put Br2. And then grams of Br2. So that's going to be the mass that is what I'm looking for. So given that, let's look at those molar masses. Pure zinc is a mass of 65.38 grams per mole. From the balanced equation, there's 1 mole of Br2 and 1 mole of Zn. So that's 1-to-1 ratio. And for Br2, that's 79.90 times 2, because it's Br2, is 159.80 grams per mole Br2. So 159.80 is the mass of 1 mole. Is the mass in grams of 1 mole of bromine. All right, so the calculation itself, 15 divided by 65.38 equals, times 1 divided by 1 does nothing, times 159.80 gives that many grams of bromine would be required. So how are we going to round that? 3 sig figs, 4 sig figs. Yeah, sorry, I know that's a really messy 5. It's bugging me now. All right, but anyway, 3 sig figs, 4 sig figs, 5 sig figs, 3 sig figs it is. So this will be 36.7 grams of bromine are required. All right, so looking at 11-7A, sodium hydroxide reacts with carbon dioxide to produce sodium carbonate and water. If that many grams of sodium carbonate are produced, then how many grams of water are made? So in other words, this is my given, that's what I'm trying to find. Let's do the reaction. NaOH is sodium hydroxide, reacts with carbon dioxide to produce sodium carbonate and water. All right, let's balance. 1 sodium, 2 sodiums. Okay, let's put a 2. 2 sodiums, 2 sodiums. That's 4 oxygen. 4 oxygen, hooray. 1 carbon, 1 carbon. And 2 hydrogen, 2 hydrogen. Hey, good, it's balanced. All right, now it says 16.9 grams of Na2CO3 times, we'll put grams of Na2CO3 on bottom so we can cancel. And we're going to convert to moles of Na2CO3 times moles of Na2CO3 are not the final answer, so I need to make sure they cancel away. The final answer does ask for how many grams of water, so I'm going to put moles of water because water is my final answer. And then the last step would be to take moles of water, put it here so I can cancel with this moles of water, and then put grams of water so that I can get grams of water as my final answer. All right, so let's fill these in. Sodium carbonate, we need the molar mass. So sodium is 22.99. So let's label what I'm doing. 22.99 times 2 plus 1 carbon plus 3 oxygens. And that equals 105.99 grams per mole Na2CO3. Let's do the same thing for water, which is going to be 2 hydrogens. That's 2 times 1.008 plus 16.00 for the oxygen equals 18.02 grams per mole water. All right, cool, I got the stuff I need. So for this, 1 mole of this stuff has a mass of 105.99 grams. Here, this is from here. There's nothing next to the H2O, so it's 1 mole of H2O. Nothing next to this, so it's 1 mole of that. So it's balanced like that. 1-to-1 ratio. For the water, 1 mole of water has a mass of 18.02 grams. So, time to calculate this out. Let's see. There we go. All right, so 16.9 divided by 105.99 equals, that doesn't change anything, and then times 18.02, and you get that. 3 sig figs, 5 sig figs, infinite sig figs, 4 sig figs, let's round it to 3. 2.87 grams of water. All right, that's how many grams of water were made. All right, onward. Because that's going to basically do the same thing. Comparing two hydrogen sources. Okay. Which one will you get more hydrogen? Find out by calculating how many moles of H2 will be made by 5 grams of each metal. Okay, so you're given 5 grams, and you're finding how many moles of H2 for each metal. Can't get anywhere till you balance, so let's check to see how things are. We got 2 hydrogens here and 1 hydrogen here, for example. So I already see I need to put a 2 right here. And then that's 2 hydrogens, 2 chlorines. Oh, 2 hydrogens, 2 chlorines, 1 magnesium. All right, that's good. Aluminum, 3 chlorine. Let's put a 3 here. And a 3 and a 2. Oh, that's not enough. All right, well, let's do this. Since that's not going to be enough, I'm going to increase the amount. I'm gonna do more of these. So let's see. Let's make it so that there's 6. So I'm gonna double this. I'm gonna times this by 3. By doing that, I now have, sorry, when I say double that, I meant 6 of these. Originally I had 3, now I have 6. Okay, so that's 6 hydrogens, 6 chlorine. Let's make that, oops, there you go, that's a 2. 6 chlorine, 2 aluminum, and 6 hydrogen, 6 chlorine, 2 aluminum, 2 aluminum. Okay, just double checking, that's good. All right. So anyway, now that I figured that out, I can do the calculation. 5 grams of each metal. Okay, that means I'm going to find out 5 grams of magnesium makes how much hydrogen, 5 grams of aluminum makes how much hydrogen. If I'm comparing 5 grams of each, whichever makes more hydrogen is the better hydrogen source that gives more hydrogen gas. So that means 5.00 grams of magnesium is going to go head-to-head in a contest with 5.00 grams of aluminum, and let's see which one gives more. Now, if I'm going to do this calculation, I need to make sure that grams of magnesium is here to cancel out this one. I'm comparing 2 different chemicals, hydrogen and magnesium here versus hydrogen and aluminum here. So I'm going to convert to moles again. Moles of magnesium. Moles of magnesium again, because that's not the final answer. I want a final answer with how many moles of H2. So I'm going to put moles of H2. And by the way, gram of magnesium cancels gram of magnesium. Mole of magnesium cancels mole of magnesium. Moles of H2 will be my answer. So I stop here. That's where my calculation is going to be. Here it's grams of aluminum, moles of aluminum, times moles of aluminum, grams of, oops, let's fix that, not grams. Moles of hydrogen. So notice, see, we're following the same pattern right here. Going from grams that were given to moles that were given, moles that were given to moles that we're trying to find. And since it asks for moles, we're stopping at moles. All right, so these will both give me an answer for moles of hydrogen. Whichever one gives me a bigger answer tells me that that thing makes more of the gas. So in order to do that, let's see, we got to fill these in. So I need the molar mass. 1 mole of magnesium has a mass of 24.31 grams. And then for the aluminum, 1 mole has a mass of 26.98 grams. Now I look at the balanced equations. For magnesium, there's no number next to the H2, so that's a 1. There's no number next to magnesium, so that's a 1. For aluminum, there's a 2 next to the aluminum. And for the H2, there's a 3. All right, so that's that calculation. Now let's see what the actual answers get. The first one, 5 divided by 24.31 equals, and then times 1 divided by 1 does nothing. So that's 0. Let's see, we'll do 3 sig figs. 206 moles of hydrogen. And then for this one, 5 divided by 26.98 equals, times 3 equals, divided by 2 equals 0.278 moles of hydrogen gas. Now, since the aluminum produces more, I'm going to say it produces more hydrogen and is a better source. All right, that's how you do it. Happy studies.